Abstract types. C++, abstraction mechanisms. Types such as complex and vector are called concrete types because their representation is part of their definition. In that, they resemble built-in types. In contrast, an abstract type is a type that completely insulates a user from implementation details. To do that, we decouple the interface from the representation and give up genuine local variables. Since we don't know anything about the representation of an abstract type, not even its size, we must allocate objects on the free store and access them through references or pointers. First, we define the interface of a class container, which we will design as a more abstract version of our vector. Class container. Public. Virtual double address of operator, int, equals 0, pure virtual function. Virtual int size, const equals 0, const member function. Virtual container. Destructor. This class is a pure interface to specific containers defined later. The word virtual means, may be redefined later in a class derived from this one. Unsurprisingly, a function declared virtual is called a virtual function. A class derived from container provides an implementation for the container interface. The curious equals 0 syntax says the function is pure virtual, that is, some class derived from container must define the function. Thus, it is not possible to define an object that is just a container. A container can only serve as the interface to a class that implements its operator and size functions. A class with a pure virtual function is called an abstract class. This container can be used like this. Void use, container address of C. Constant sc equals c.size. For int I equals 0, I not equal sc, plus plus I. C out c, I, new line. Note how use uses the container interface in complete ignorance of implementation details. It uses size and square brackets without any idea of exactly which type provides their implementation. A class that provides the interface to a variety of other classes is often called a polymorphic type. As is common for abstract classes, container does not have a constructor. After all, it does not have any data to initialize. On the other hand, container does have a destructor, and that destructor is virtual. Again, that is common for abstract classes because they tend to be manipulated through references or pointers. And someone destroying a container through a pointer has no idea what resources are owned by its implementation. A container that implements the functions required by the interface defined by the abstract class container could use the concrete class vector. Class vector container, public container, a vector container implements container. Vector v. Public. Vector container, int sv, s, vector of s elements. Vector container. Double address of operator, int I, return v, I. Int size, const, return v.size. The public can be read as is derived from, or is a subtype of. Class vector container is said to be derived from class container, and class container is said to be a base of class vector container. An alternative terminology calls vector container and container subclass and superclass, respectively. The derived class is said to inherit members from its base class, so the use of base and derived classes is commonly referred to as inheritance. The members operator and size are said to override the corresponding members in the base class container. The destructor, vector container, overrides the base class destructor, container. Note that the member destructor, vector, is implicitly invoked by its class's destructor, vector container. For a function like use, container address of, to use a container in complete ignorance of implementation details, some other function will have to make an object on which it can operate. For example, void G vector container VC 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Use VC. Since use doesn't know about vector containers but only knows the container interface, it will work just as well for a different implementation of a container. For example, class list container, public container. List container implements container. std, list ld, standard library, list of doubles. Public. List container, empty list. List container, initializer list ILLD, IL. List container. Double address of operator, int I. Int size, const, return LD size. Double address of list container, operator, int I. 4. Auto address of x, LD. If I equals 0, return x. I. Throw out of range, list container. Here, the representation is a standard library list. Usually, I would not implement a container with a subscript operation using a list, because performance of list subscripting is atrocious compared to vector subscripting. However, here I just wanted to show an implementation that is radically different from the usual one. A function can create a list container and have use it. Void H. List container LC equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Use LC. The point is that use container address of has no idea if its argument is a vector container, a list container, or some other kind of container. It doesn't need to know. It can use any kind of container. It knows only the interface defined by container. Consequently, use container address of needn't be recompiled if the implementation of list container changes or a brand new class derived from container is used. The flip side of this flexibility is that objects must be manipulated through pointers or references. Thank you for watching. Subscribe.